Good morning, everybody. Welcome to our machine learning seminar. Today, we'll have a talk from Sahar Niknam, who is a doctoral researcher at the VR/AR lab at the Department of Computer Science, Faculty of Science, Technology, and Medicine of the University of Luxembourg. And we'll have a very nice and intriguing topic on adversarial examples or adversarial attacks on neural networks. Sahar, the virtual floor is yours. Please go ahead.
Thank you very much, and welcome everybody. So I'm currently working at the VR/AR lab, but this presentation is going to be first. It starts with a short and very selective introduction to adversarial examples, and it will end with a research that I was doing during my master's study as more like a hobby. So, and one more thing before I start, I really like you to interrupt me whenever you have a question or when I'm not clear, because I would like it better if the presentation goes in a form of a conversation rather than me just talking. So, adversarial examples. This is literally the first images that we had from adversarial examples, and as you can see, the first columns, both first columns are images from the ImageNet dataset, and the middle columns are adversarial perturbation magnified 10 times. And when we added these perturbation to the ImageNet, to the samples of ImageNet, this is the example is worked with Alexnet. Alexnet classify them, all of them as ostrich. And it was a shock when they introduced this work in 2014, because Alexnet won a huge prize almost a bit less than 2 years before that in 2012, because it hit like a huge, like a really good record in classifying images on ImageNet dataset. And it was like ChatGPT of its time. So you can imagine like the mood after they discovered that Alexnet could be fooled so easily by adding some very small perturbation to ImageNet dataset that we can't even see. But then adversarial examples get a bit more interesting, because instead of being just some image files in the computer, they start intruding our worlds. So this is a 3D object, which can fool Inception network and impersonate itself as a rifle. And the interesting part is that if you rotate an image and feed it to Inception ImageNet dataset, like if you rotate it for almost 30 degrees, the ImageNet failed to classify that image. While we can see that with the 3D printed object, it can almost fool the network from every angle. So it's something really new. But by then, it was all in academia, but the paper adversarial patch made a huge fuss when it was out, it was released, because as you can see, we have the actual image of a toaster next to a 3D object, a banana, and the network is not fooled. But when we put a smaller patch, a weird patch next to the banana, the network is fooled and classified the image as a toaster. I mean, they presented the work with a toaster patch, while we have all sorts of other patches, and actually you can create one for yourself. This is the time that it got very serious, because researchers start to creating or thinking of like use cases which could be troubling actually. So the three people in the first row are the authors of the paper, and they created an adversarial patch or example. When they print it out and put it on like a frame, like a glass, like a frame for glasses, they could successfully impersonate people in the second row, which two of them are famous, but one of them is the author of the paper actually. And the interesting part is that they trained a deep network on like as few as 30 images of one of the author, and they could still impersonate that person with that glasses. And here the researchers are getting even bolder and trying to, like they actually claim that they are trying to fool surveillance cameras with this adversarial patch. So when you put it on, you hold it, you are not going to be detected as a human. And even more troubling cases is those that are involved in fooling some critical autonomous systems. For example, we have this sign on the left side, which is a normal stop sign with some graffiti on it, and the one on the left side is carefully carefully engineered with some stickers to fool a neural network to believe that it's a speed limit 45 miles per hour. And it is dangerous because if someone sees something like that, they wouldn't notice something strange, and it could be completely overlooked. So I'm going to explain, talk about 3 papers in the field. The first two one that in
one question. I have one question.
There's a question.
You asked for interruptions, right?
Yeah,
so are there also examples for these adversarial attacks that are outside the area of image processing? Are you aware of examples?
Like for example, like voice, for example.
Yeah, for example, yes, exactly. Any other application?
So I believe with deepfakes are also no, that's the reverse part.
Yes.
Just let me think. Can you give me an example?
No, but I was wondering because also I knew these examples from image processing, and I was wondering when I saw your further examples how if the same idea could be applied elsewhere. For example, I mean, I just making stupid things up now, right? But maybe a molecule could belong to a certain class of molecules, and you make a modification that keeps it there, but for the network it's in another class, or
like that. Okay, so I mean, I remember. Yeah. I remember I was doing another presentation for adversarial examples, and I started with explaining how the history of adversarial examples. And one of the the earliest adversarial example was the ones, the emails, the spam emails or advertising emails that try to fool email server that they are good emails. So I guess that's that's also a type of adversarial example, right?
Yes, thanks. Yeah, exactly. I was thinking exactly, for example. Yeah, thank you. That was.
Yeah. So I'm going to discuss 3 papers, and the first 2 papers that introduce adversarial examples, and the other one that is my favorite. But for those of you who are interested but not worked yet with adversarial examples, you have to be careful that there's a huge chunk of diverse research that I'm leaving out because I'm trying to explain something about my own research, which is more related to these 3 papers, and they are my favorites. So be careful. But the first paper that explained or introduced adversarial examples was was blaming the whole problem on nonlinearity of the networks, but they mentioned it nonlinearity, but in fact they meant non-continuity or discontinuity. So, for example, they introduced that we have an image which belongs in a m-dimensional space, which m here is the number of pixels available in the image. For example, for MNIST dataset, that would be 784. So that's it. And the network is, in fact, or basically a function mapping a sample of that image to a discrete list of labels. And you also have the loss function, which also maps an image and the label to a real number greater than 0. So we know that loss function here is a continuous function and a linear one. Then we have perturbation, adversarial perturbation, which also belongs to the domain of image. So it belongs, it is a member, it is a m-dimensional space. It's coming from an m-dimensional space, and we want it to be to have a minimized value. Here, in that paper, they used Euclidean node. And while we want it to be minimum, because we don't want the perturbation to be visible to human eye, we want it to be that big that change the label. So here, we want to feed the perturbation plus the image to the function, and we want the output to be a label different from the actual label that we are going to get from the image. And the other condition, which is trivial, is that the sum of perturbation and image should be in the bound of the valid values for image. So here we have 0, 1 because it's a normalized picture. Okay. If you have any question, this is a good time to ask because I feel like I'm short of breath right now. No question? Okay then.
So sorry. So there is no mention about the distance between the cases. Like if we think about misclassification, you have some examples, and they can be very different from one another, or they can be very close to one another. So in this proof or theorem or whatever you are going to show, there is no mention about how different the cases are in the training data.
Different, you mean difference between the adversarial example and the actual image?
Exactly.
So that's here. We want to keep it minimized.
The perturbation itself, right? But the difference between the images that were used in the training are not somehow related to that.
I didn't add it here because they actually define the finding a minimum distribution function, which gets the image as input and the label as output, and they tried the LBFGS optimization algorithm to minimize it. But the whole idea is to keep R small.
All right.
So if we keep the perturbation is small, because this is the adversarial perturbation, this part inside the function is the adversarial example.
What I mean is that if you have a different image like Y, there's an X, which is the input, the image, right? And if you had a different image Y, that is also in the training data. And the question is, what is the difference between X and Y?
Oh, okay.
The norm of the difference and how it relates to R, the norm of the R.
In that paper, they didn't do that.
Oh, I see.
But we definitely have, we have other attacks that consider the distance between the actual images for that label as well.
Okay.
I guess I
Could
didn't
you expand a bit on the explanation of the authors?
Sorry, what?
Oh, sorry. You mentioned in the beginning that the authors now give the non-continuity argument, but could you expand a little bit on that? How that
Yes,
works?
yes. This is that part that I'm going. So here is the loss function, and we know that loss function is always going to return a value, a real value greater than 0, and it is continuous, kind of, because it changes a little by little. On the other hand, we have this is not an accurate representing. This is just for illustrating the idea. So here we have a class which has very sharp boundaries because we have a finite number of labels. So the output of the network as a function is discrete. It's either 1, 2, 3, or 4, for example, for 4 classes, right? So at one point, when a loss function, for one example, for an image, falls in that boundary, it starts labeling it as one object, for example, a cat. Then as soon as we hit it, this border, this threshold, it starts to label it as another thing, while the loss function is not changing as much, or it's not changing in a discrete way. So was that clear?
Yes. So if I got it right, then you're saying I have to just jump a little bit over the table boundary. The loss will be almost the same.
Exactly.
Whatever. Yeah.
So in that paper, they actually mentioned a lot about the concept of decision boundaries, which are these thresholds, and their idea for creating adversarial examples is to work around decision boundaries, because loss function, we can have any values for loss function and we can play it here smartly. So to fall one example from one class, to move one example from label cat to another category. But their workplace is really small at decision boundaries. So the next paper is the next important paper in that scope is from the same team, interestingly, but this time they claim that it wasn't really accurate to blame discontinuity. Oh, let me add something here. So this paper was published in 2014, almost early, and it was about the time that people stop using sigmoid activation function and start using ReLU function. And ReLU function is not continuous as a sigmoid function. The move was because of the vanishing gradients, and that was, I guess, the motivation behind the authors blaming specifically activation function, ReLU activation function, and also softmax at the end, because all of them contribute to discontinuity. So the whole idea in this paper was that we have a continuous space for our concepts, for the concepts that are fit into the network, and the network somehow with its activation function and the softmax layer crash it down and spread it over, and then build it another time, build it again into different like histogram bars. So it kind of crashed the continuity of data that we are feeding it, and so that's the reason that they can be easily fooled, because we can work in the decision boundary, the discontinuity. So this is the next paper, and this is a really nice paper. This time, the same team tried to explain that discontinuity may be not the main culprit, but the linearity of the network is problematic. So they started explaining that when we feed an actual image, and like the image of an object, one concept to the network, we are digitizing that on so many levels. We just, for example, we have values for each pixel. The value for each pixel is between 0 or 255. So the unit of change is 1/256. So for the values smaller than that, network learns to ignore them and jump over these gaps. And for that reason, we are going to have a value eta that we can add it to one image and have our adversarial example. And we can manage to keep it, the infinite norm of the eta below a threshold of, below a value of epsilon. So when we do that, imagine we are going to feed it into one layer. So it's this is the weight vector. And the output of that layer is weight vector times the input, the image. So if we expand that, it's going to be transpose weight times x plus eta. And then if we expand it more, we are going to have the actual output and this term. So the idea for creating an adversarial example was to use this term and maximize it without maximizing the actual value, because we already set a threshold for that. So this is this is infinite norm. That means that none of the values inside this vector or matrix should be larger than epsilon. So the nice idea that they used for creating adversarial example was to use the output of sine function of the vector as eta. In that case, the term that we were talking about will become weight transpose times sine of weight vector. So now we imagine that, let's imagine that weight.
Sahar, what do you mean by the sign of the weight vector? Is it a component-wise sign or?
No. It just takes, it's a function takes all values, and if they are negative, return -1. If they are positive, returns 1, and if they are 0, returns 0.
But this is the component-wise multiplication, or this is the?
Yes.
I see. So it returns the vector.
Yes, exactly.
Mm-hmm.
And so the result of this is going to be a value, one scalar value. Right?
Okay, so this is like a sum of absolute values.
Yeah, exactly. Two vector times. So, sorry, I guess. But okay, the outcome is going to be one scalar. And imagine we are going to have like n elements in our weight vector with an average size of m. So the result, this multiplication result, going to be m times n. And n is the dimensionality of the data, the image. So if we try to feed, for an image of like 20 for the MNIST data set, which is 28 by 28 images, n is going to be 784, which is very large. So how even a small m's going to produce a large value for vector times eta term. And if we increase the dimensionality of the space, or like in simple word, if we make images larger, we are going to have a large term, a large value, or which means a large diversion from the actual label that we are going to get. And this doesn't affect the actual value for eta. Question? So this is the last. Let me see if yeah, everything's okay here.
But again, what because this is the result of their work or paper, the conclusion, or how does it link to the
because
to the adversarial attack?
Okay, so we find a way to maximize to change this value and increase it without changing eta, right? Because no, I mean, if you're okay with this step, here we had this term, which means image fit to one layer, for example. And this is the weights vector for one layer. And here is the value that we are going to have for when we feed the actual image, the original image to the layer. And this is the term that is caused or is added to the output of the layer because of the perturbation here. We saw that with using the sign function, we can maximize this term.
Yes, but in this example, it is quite nonlinear. I mean, the eta then is it depends on the weight itself, right? So it is a function of the weight.
It's a function of the values of weight, but it's going to be increased because of the dimensionality, because of the dimension of the image, not the weights itself.
Mm-hmm. Okay.
And this is actually the base of the, they call this method fast gradient sign method, which is the basis for a method that I used for my own research. And it is much faster than the method in the previous paper. And yeah, it's a really good and very really genius idea to use perturbation to replace perturbation with sign of the weights. But it is, that is the like white attack because we have to know the weights. So this is the last paper that I'm going to discuss. This is the paper. The title is Adversarial Examples, Bugs or Features. So this is a paradigm shifting paper because it tries to explain that why are we looking at adversarial example as bugs? Because it is just more sensitivity to data details that we as human can't perceive. So this is very in line with what I did in my research. And in fact, they always talk about that this sensitivity is an opportunity. The discovery of adversarial examples is an opportunity to fix them, while the discovery of adversarial examples is an opportunity itself. So we can use it. We can use the sensitivity of networks for our benefit. We don't need to fix it. They just perceive the information or the word in another way. So that was the actual motivation behind what I did. So it's just the implementation of, it's an extension of the fast gradient sign method in the second paper that we discussed. This is a simple training loop for a network. We usually use it as a line, but I opened it because I wanted to change stuff, because the algorithm says that we have to change stuff. This is not mine. This is just copy pasting. So here is the part that we work with the gradient descent. Usually we use the weights. We use the gradient on weights. So we try to change the weights of the network to train it. But in this method, we change input image. So we get a prediction from the model that is already trained. So we are not going to train it on the input image. We got a label. This is the label, the prediction. And then we calculate the distance between input label and the prediction. So we got input label as an argument here. And we calculate loss. Then based on that, we try to change input image gradually until we get the loss, we get the label that we are looking for. Although I use different stop condition here, I try to minimize loss between the prediction and the label, or stop it after a while. because sometimes you can create adversarial example.
So may I ask a question to be on the same page, if I understood correctly what you're trying to do? So you are trying to optimize your input, so you compute the gradient with respect to the inputs in order to change the label to some chosen another one.
Exactly. I want to feed the network with one image, and it's going to predict one label for that. I'm going to change the image instead of the weights. Usually we change weights because we want to train the network, but now I'm going to change the input image until I get the label that I want.
So you can have a model, and once you have a model, you could use any model practically.
I need to have a trained model.
Trained model, yeah.
Yes, exactly. I train the model.
And also you need to somehow have it in a form that you can compute this gradient somehow. You can.
I didn't get it. Sorry.
So I mean, let's say if you have a TensorFlow implementation, you can get the gradient for free by applying KD. But if you have a black box model that you can only use the predictions, perhaps you could do some final difference thing.
That's a white box attack when we have access to everything, to weights and inside. We are working inside the machine, not outside. It's not a black box. So first, my idea of doing that was what I did was to feed the network with noise, with Gaussian noise, and ask the network to, can you see behind, because I see something that, so then with that implementation, I start feeding noise to the network and ask it to optimize or change the input image until it gets a desired label for that. It returns a desired label for that. For example, here 4. And to me, it was like after we train the network, this is like a playing dough, and it's going. The network is going to change it and shape it in the form of 4, what it perceived as 4, as the letter 4. The number digit 4.
So a question. So if you do this, it will classify it as 4, but it would be on the bare fringes of this class distribution, right? It would it's just because your algorithm. Wait, where is it? It stops when you reach the label, right? So it basically it's not how to say, it's not an archetypical image of 4 of the network. It just barely classifies it as 4, right?
Yes. This is like I mean, no, this is not a technical. The image on the right is not a technical description, but it is my idea, because when a network, I mean, I can argue how what is number 4, the concept of 4 in the network, right? The only way that we can understand how it looks at an image and detect as 4, is to actually feed it something to network and get the label. If the label is 4, it's 4 for the network, right?
I can also, okay, 2 things. I had your image in mind from the previous slides, right? Where you had like a classification boundary. And if I understand your algorithm in the left part of the screen correctly, you will just enter this class, but then, right? So this is what I mean with barely a 4. And the other question would then be, how about uncertainties of such neural networks? I mean, if this goes too far away, please stop me. But it's like, have people incorporated that, right? Because now people also use some measure of uncertainty of the prediction, and
yes,
can you still fool them?
Oh, you can. You see, I set 2 stop condition here. One is iteration, because you can't wait. You don't have time. You can wait. I mean, sometimes it doesn't create adversarial example, so you want to stop it anyway. This is I don't know, a safety measure here. And then loss. So loss here is a really important measure, stop condition for me, because we also use loss for understanding if a network is actually doing a great job in classification, right? It's not always about accuracy, it's also about loss. But I also added, I mean, this is one version, but I also added confidence, like how confident is the network that is that the classification that the image is number 4, digit 4, and also another one is whether it actually is can change it and get the label, because sometimes you don't get the label because I added this condition here.
Yeah,
so,
yeah, my mistake. I mislooked in the code. Yeah, so you can control basically how sure it is.
Exactly.
Yeah,
And what I did was to actually, after I trained the network first on the MNIST data set, we have a benchmark, right, about the accuracy, about the confidence of the network. I guess used that, but I really like loss better because it's more accurate. And I measure the loss for classification of the numbers in the MNIST data set with the correct classification, and use it as a threshold for my adversarial examples. So when it reached that loss, it means that now the network is as sure as it could be.
Yeah, it's 3 to the minus 10 to the minus 2, sure, in some sense. Thank you. Please.
Sure. Thank you. So what I get was first here, this is the adversarial perturbation, in fact, for number 5. So here for this row, I feed the network with a Gaussian noise, and I created like 10,000 of 10,000 adversarial example, not perturbation, example for each for class 5, and then average it. So this is an average image of all adversarial examples of class 5. And this is just feeding the network with noise, and then have the adversarial example, remove the noise from the output adversarial example and get the perturbation directly. And this is when I feed the network with 0 vector. So I didn't need to reduce the input from the output. So this is basically the output. And as you can see,
can you let's say repeat it or elaborate on that, because I'm not sure if I understood it correctly, what you did. So I mean,
so
what were the inputs, and what was the training, exactly, and what was the prediction in your case that you are showing?
I had two inputs. One was 0 vector, simply an empty blank image.
But this was the input for your algorithm to prepare the adversarial.
The input image that I feed to create an adversarial example was an empty vector, 0 vector.
Mm-hmm.
And another one was I created like Gaussian noise and feed it to as input image. So like blank, okay. No semantic in the image. In one trial, I created like more than about 10,000 adversarial examples and get the average to get to for the
10,000 for different white noises at the input, or
yes, with different white noises, yes. Okay. And then here it's just one adversarial example which I get, and then this is adversarial example minus the input image, but for one adversarial example. This is also for one adversarial example, but it is fed with 0 vector, so the output is the same. So, and as you can see, they're all similar for the class 5, and A, B, C are 3 different networks. One, I guess, I tried with CNN and feed forward, but they are really small, not big one. So feed forward with I don't know, like 7 at most layers, and CNN with 3 blocks, I guess, 3 or 5 blocks at most. But this is so clear, and it is just with feed forward. And then I try it for all the classes in MNIST dataset, and as you can see, this perturbation are the same over different networks and with different methods. But it is not something new because we already knew that adversarial examples are generalized over, I mean, with one adversarial example, you can fool all the networks. Was there a question?
No,
Okay.
sorry, I forgot to switch off my mic.
Sure. Then, so this is an overview of different networks with different activation function and different optimizer. And forget about the first row. These are all perturbation. And as you can see, this is more clear with SGD optimizer rather than Adam, and also with feed forward rather than CNN. And this is for FMNIST, fashion MNIST. This is not clear as MNIST, but I would say I can still see some similarities. And what I did for the next step was actually based on two motivation. First, you see here I can see some. I mean, I couldn't believe that these are just noise. I mean, we know that adversarial examples are not just noise, and some argue that they are artifacts of network learning. But for me, it was more meaningful than that. I knew that the semantic is somehow related. I feel like I could see that the semantic is somehow related to the actual shape of the digit. And as you can see, it's also very clear that adversarial perturbation are getting really close to the actual digit. So for that reason, I did another experiment. What I did was to calculate the average of all digits in class 5 minus the average of all digits in all other classes. That was the result. I called it difference, positive negative set difference. And with a bit of noise, this is exactly perturbation that we had for the class 5, but it's inverse. Is the process here clear? Should I go to the?
It is clear what you did, but it is the conclusion is not clear because
I didn't reach it.
in former case you had some white noise, and here you have some specific example.
So, yeah, the reason that I did that because I was trying to find what these this shape mean, if they are semantically meaningful and relatable to their actual classes. That was the reason, the motivation. I'm going to the conclusion in next slide. But for now, I just want you to see that these are the first row are the difference between the positive and negative set for each class. And they are really close. They are really like the actual perturbation. So here you can see that this is the difference between positive and negative set, the contrast between the positive and negative set averages, and this is the perturbation. So with that idea, I came to that conclusion that maybe the reason that a network does recognize this adversarial perturbation as digit 5, maybe it's only because of the categorical learning, because they don't when a network is learning, it doesn't learn the concept or the shape of digit 5 only from the positive samples, but also from the negative samples. So positive samples and negative samples combined together describe the word for the neural network. And the reason that I don't fall for this adversarial perturbation as a human is that because not only I know how digit 5 looks like, and I know how all the other digits look like, but I also have billions of more concepts. I learned them that I can describe this shape with them, right? So when I see that shape, I may interpret that as a face with two eyes. But for the network, the world of concepts is so small and so sparse that it has to interpret that shape with one of the classes. It has no other option. So it tries to find the closest one to that shape. So with that, I did one final experiment here. I created a data set of literally 4 samples. First row is my data set. 4 sample, 4 classes. And as you can see, this is the object, the square, and they are overlapping. If you consider the class 0 and class 1, they are overlapping, plus put them all together, they are not covering the whole space of the data set. I created the positive negative contrast set, also perturbation, adversarial perturbation, nothing strange here. But then I also created another data set with 4 objects, 4 samples, that they actually cover each pixel in the data space. For example, this pixel here is going to belongs to the class 0, and it doesn't belong to any other class. Plus, every pixel in the space, in the data space, in the word space of the data set, belongs to one of the classes. They are not left unassigned. Then I created the positive negative contrast set, which obviously is the same, but the most important part was the adversarial perturbation for such a data set is exactly the same as the sample of the class. So in such a world, you don't have adversarial example. And thank you.
Thank you, Sahar. There was a discussion during the presentation, and I think it was very thought-provoking and set our mind in the proper concept based on the evidence that you provided, literature-based. And I think it is a nice way to look at it. From my perspective, I have some questions, but maybe first I will try to leave the floor for others to ask questions. So please switch on your mic or raise hand if you like to ask a question. And so maybe before that, I have 2 actually questions. First of all, is it of general nature, and it is related to what you showed in the end, meaning that perhaps there is a too little gap between the cases, and perhaps it would be useful to have a lot of different concepts, meaning different numbers and objects, which should be classified as not sure, right?
Yes.
And maybe this could improve this performance of the network against the adversarial attacks. So that's my, let's say, first observation. And
yes, we probably can have a data set that because I mean this is for example, as small as an example of images in MNIST data set is 28 by 28, but the data space has 700, almost 800 dimensions, so it's not easy to cover it all. So for example, we can present too many shapes and too many concepts apart from the digits, but the network has no knowledge of that. So I mean, they are excused to be fooled by adversarial example, and the problem is that their word is really sparse with concepts.
Yeah. Matthias, please go ahead.
Yeah, thanks for this talk. So one question would be, these were all classification examples. Is there also work on regression
No. Another big limitation is that I didn't work with the bigger neural networks. Maybe learning is different there. Maybe it's just because I use small networks. And definitely no regression.
And in the literature, is there any work on adversarial attacks for regression models?
I'm not sure, sorry.
And so when I'm trying, okay, when I think about such networks, I think, okay, I have this large input space, like for the NIST, like you said, and then I have some sparse data in this space, which lies on a manifold, and the network somehow tries to learn that subspace, right? Now, and I thought, okay, if I move inside the subspace versus I move away from the subspace, for example, that this somehow was related to the attack. But is that true? After now I'm also now I'm not so sure anymore. Is this somehow related to the geometry of the data and how you when you perturb your input, how you move along that manifold or away from it?
If we are talking about image classification, definitely, because we have, I mean, the thing that I was trying to investigate in last silly experiment was to make sure if I can actually give a rich, because I couldn't actually practically give a rich data set, geometrically rich data set to the network. So I tried to work it on a small word with small concept, but somehow that they are covering the whole data space. Am I getting your question correct, or?
Yeah, but that's kind of the extreme event, right? You have a very small input space and you can basically learn all of it, right? But then as soon as you increase the dimensionality of your input space, you cannot cover it anymore with data.
Exactly.
Because simply
it's concept parse the actual data set that we are using for the network compared to the dimensionality of the data set, dimensionality of examples.
And then, yeah, and then automatically you have this, you have more parts of space, or directions where you can go that just is no data. Yeah, like in the, yeah, okay. It's. I think I cannot formulate my question very clearly, but thanks. Thank you.
Thank you.
I was trying to relate it to somehow to a kind of try to relate it more explicitly to the idea of having a manifold in a higher dimensional space, and that you have many directions where you can go that are not covered by your data, and how that is related to this type of adversarial attack. But that's as close as I can get. I cannot really formulate a good question. But thanks for the talk.
Thank you.
So I may have one question. What do you think about improving the training or improving the architecture of the network to prevent those kind of adversarial attacks? Do you know about the literature examples, or do you have some ideas?
So the first, obviously the first thing that they did was to add an adversarial example to the data set, but it's really ad hoc and not a good way to do that. But to be honest, as far as I followed the literature, it was always about make the robustness by adding adversarial examples, not like I'm not sure if there's something else. I didn't read it thoroughly, but as far as I know, it's always about making it robust by adding examples of adversarial, adding to enrich the data set. So
I see. Because in this regression networks, there is a concept of physics informed neural networks in which you enrich your loss function or the architecture of the network itself in order to explicitly apply a priori some laws, let's say rotations, framing difference. And do you think it could help here to have it.
Rotation, by rotation, you mean?
You mean, I mean that the image and it's all the rotated version of the
Okay,
image.
augmenting data set.
Well, but not in the data set, but maybe in the loss function itself or in the architecture of the network.
The problem with augmenting is you need too many samples. And what Jakob says is if you put it in the architecture, you can do it without samples, basically.
Yes, yes, but I mean, okay, yes, but no, I have no idea.
All right.
I follow up to that. So would it be fair to say that the higher dimensional your input is, the more of the possible attack vectors you have? Is that right?
I believe so, because this is also the claim of the second paper. I mean, I believe that they are more accurate in the second paper that they introduce adversarial examples with. So they blaming the high dimensionality of data partially. They still try to stick with the linearity thread, but they mentioned that high dimensionality could be the problem. But from what I found, high dimensionality is the main problem. Not problem, but like the word is too big for the neural networks. The concepts are small. They can't cover it. They can't enumerate the word for them.
If that is true, then data augmentation is basically failed, as it cannot succeed then, no? Because if your input space is large enough, and if that really means that the number of possible attack vectors is also very large, then you cannot fix this with data augmentation.
You said augmentation has failed?
No, I mean, and I'm saying if really with the number of possible adversarial attack vectors increases with the dimensionality of the input space, then you cannot use data augmentation to fix that, right? Because you would just need too many data points.
To be honest,
off there.
No, I mean, to my knowledge, augmentation is actually helping, and it's like filling the space, the data space, the concept space of the network. But it's
that should be harder and harder the higher dimension of your input spaces, right? Or is there something else?
But Matthias, maybe the helping hand is from the network itself, because there is a finite capacity of the network. So if you augment the data large enough, then your network will be, will need to fit somehow into that data. It will not be able to overtrain, or how to say,
but to be honest,
overfit.
I have one thing to add. I mean, this is the same situation for humans, right? Because we can detect many objects because we have many concepts, and if we see something really strange, we are going to be puzzled by that. We can classify that. So this is the same problem here. I believe that this is just because we have a rich concept world, but they don't have. So augmenting data set, I guess, help, because it adds to the concept, the set of the concept that they have, or enrich each concept. I'm not sure if I get it correct.
And the network complexity itself is, of course, also.
Maybe it also adds this notion of distance from the test training examples, because it gives you the sort of the training example plus the vicinity in the same class. Maybe it helps from that point of view. Matthias, you wanted to?
Yeah, maybe, I don't know. but it was an interesting discussion, and thanks for the introduction to your work and the adversarial example.
Thank you.
Thank you, Sarah. It was indeed thought-provoking and instructive. Thank you for preparing this to us and for answering all our questions. And thank you all for attention and discussion. We'll have 2 weeks break because of the Easter break at schools, and so I will not organize the seminars for the next 2 weeks, and we'll meet in 3 weeks on it. I believe it is 19th of April. Anyways, have a good day and good Easter break, whoever has holidays that time. Bye bye. Thank you, Sahar.
Bye.
Thank you. Bye bye.